Hello and welcome to this J4K online session. My name is David Delabassée and I work at Oracle in the Java Platform Group. Today we're going to discuss running Java virtual machine into containers. Don't worry, you haven't missed part 1. There's no part 1. Part 2 simply means that the content that you're going to see today is up to date. So 2020 is an important year for Java as it marks its 25th anniversary. So since 25 years, Java has been developed based on two core principles: developer productivity and application performance. That evolution has been done in the face of constantly evolving factors, such as programming paradigms. For example, since Java 8, we can see that Java is getting more and more functional programming capabilities. Application styles. Years ago, we were developing and deploying multi-tier client-server application. Those days, it's mostly about microservices. The hardware is also evolving. For example, we have access to new architecture, such as ARM. Our Java application has access to more and more CPU, more cores, more memory, but also GPU, for example. And last but not least, the deployment styles are also evolving. Years ago, we were deploying application on top of application server in our own data center. Today, we are deploying mostly REST-based microservices into containers into the cloud. And that's what we're going to discuss today. One of the deployment techniques that is widely used today, and that is container. Now, given that you're attending a J4K, I'm pretty sure that I don't have to spend time on explaining what a container is. The only thing that I want to mention is that today I'm going to use Docker for my demo, but anything that I'm going to discuss today in terms of techniques and trips apply to any container runtime that is using Linux CGroups and Linux namespace. So those are two Linux technology which most of the container runtime are leveraging. So that applies to those as well. So let's have a quick demo. Hello containers. So for that, I'm going to switch to this. So let's see. So what I have here, I have Docker running on Mac on OS X. So my Docker is configured to use 3 CPU and it has access to 1.5 gigabyte of my underlying host. So let's see. I have a simple Docker file. It's the most basic Docker file that you can have. So basically we used this base image, then we copy the hello.java, we compile the hello.java class, and we run the hello.java. So let's have a quick look at hello.java. It's basically a simple hello world. So let's build that. So docker build -t, this is going to be the demo, and this is the context. Okay, so this is our Docker run, and we can run obviously that Docker image, and this is the result. Nothing very fancy here. Hello world. What we can do, we can check. Let's see, demo, Docker image demo, and we can see that okay, this image has been created 19 seconds ago, and it weighs over 600 megabytes. So that's an issue. Because to run this simple hello world application, the Docker runtime has to fetch over 600 megabytes from a Docker registry. So that's something that we're going to discuss a little bit later in this session. But that's basically the most basic hello world that you can have. So let's go back to the slide and let's move on. We're going to come back to that later on. So the first thing that I want to discuss is JVM Container Awareness. So if you look at these slides, you can see that with each Java release since Java 8, basically, we are making the investment in OpenJDK to make sure that the hotspot virtual machine is aware of the container it runs on. Why this is important? There are multiple reasons, but one of the most important one is what we call JVM ergonomics. So JVM ergonomics is basically the ability that the hotspot virtual machine has to auto-tune itself. So when it runs, when it starts, the hotspot will basically look at the environment it runs on, and based on that, it will configure itself to provide a good behavior. So it will look at the number of CPU it has access to, it will look at the RAM it has access to, and it will configure things such as which GC should be used, how many threads do we have for the command for join pool, and so on and so on. So if you don't do any tuning out of the box, you will have a behavior that is good. So why this is important? Well, let's go back to a demo. So we still have this Docker, the So Docker run demo. So this is our hello world. Now, remember that my Docker is configured to use 3 CPU and it has access to 1.5 gigabyte. What I can say, for example, I can say that, sorry, first I'm gonna switch. So let's see, I have this hello world. It's basically the same hello world, but this time this hello world is looking at some environments metrics such as the number of CPU and so on. So we're gonna update the Docker file to use this one instead. So hello2, let's compile it and let's run it. Okay, let's run it. Okay, so Docker build -t demo. So I'm rebuilding the Docker image. We can see that this time hello2 is being used. So if we run that, so Docker run demo. I said demo. Okay, this is the hello world, but this time we have some information about the environment. We see that it's a 1.8, so it's a quite old virtual machines. It runs within a container, so that's good. It sees 3 CPU, so that's good because my Docker has access to 3 CPU. And the command for join pool is configured accordingly. So basically number of CPU -1, that's 2, okay? And that's the CPU that the JVM, that hotspot has access to. So what I can do, I can still run that, but this time I can tell Docker, okay, I only want to use 2 CPU out of the 3 CPU that you have access to. So basically the container will be physically limited to only use 2 CPU. What we see here is that the code, so the Java code running inside the container still see 3 cores. And worse than that, if we log to 1 CPU, so 3 cores, so hotspot will be configured, so sorry, the command for join pool will be configured to use 2 threads. So that's clearly an issue. We can also say that we only have access, for example, to 64 megabytes. And all the metrics are wrong. Why? Because this particular version of hotspot is very old, and that version is not container aware. So basically that version of hotspot is looking at the environment, the host environment. So it sees that it looks at the host environment, so it's not able to get to use the metrics coming from the containers. So basically the JVM ergonomics are completely messed up. So very quickly, if you run an application within that environment, chances are high that it will be killed by the Docker runtime, because it will basically try to overconsume resources. So how can we fix that? Well, that's pretty easy. Let's see. So the way to fix that is basically to use a version of hotspot that is container aware. So I'm going to use OpenJDK 16, which is the latest one, which is still in early access. So Docker build -t demo. So let's see, it has been rebuilt, and now let's run, so 1 CPU, 64 megabytes. So let's see what the Java code inside sees. So it's running inside Docker, it only has access to 1 CPU, and the command for join pool is configured to use 1 thread, and it has only access to 30 megabytes. So everything is good. So we can see that if I increase those values, so for example, I say that my Docker has 2 CPU, again, the ergonomics are correct. So it sees 2 CPU, so the command for join pool is configured to 1 thread, and it has access to 133 megabytes, and so on and so on. So if I say again that we have access to 3 CPU, we'll see that the command for join pool will be now configured to use 2 threads. So that's basically, this shows you why it's important to use a Java virtual machine that is container aware. Why? Because of the JVM ergonomics that we just saw. So let's go back to the slides. Okay, the next thing that I want to discuss is performance. Performance is basically latency, and there are 2 angles to discuss latency. The first one is the time it takes to start the containers, and the second angle is basically the time it takes to start the application, so the Java application running into the containers. So when it comes to starting containers, we have to keep in mind that a container is made of different layers. And if we look at the Java application in a containers, at a very high level, there are 3 types of layers. There's the Java application layers, there's the Java runtime layers, and then there's the lower layer, which is the operating system layers. And the goal, if we want those layers to those containers to start as quickly as possible, those layers have to be as small as possible. Why? Because anytime that image has to start, all the bits have to be fetched from the registry. So obviously there will be a difference if your container image weighs 100 megabytes or if it weighs 1 gigabyte. So the goal is really to try to reduce as much as we can the size of those different layers. So if we look at the Java layers, there's not much that we can do. Obviously, there are some best practices, like for example, watch out your dependency. Don't make sure you are not embedded the whole internet with transitive dependency when you build your applications. Try to leverage as much as you can the cache mechanism that the containers provide. So it's basically striking a balance between having different layers and layers that doesn't change frequently. So if you have layers that doesn't change frequently, like dependency, maybe it's a good idea to put those dependencies in a separate layers so that you can use the caching of layers. That's also why maybe fat jar are not really a good idea, because if you change one single byte in the jar, it has to be, basically the layer has to be recreated and it has to be reloaded. So that's something that you have to think about. And then there's also CDS that we're going to discuss later on. Now, if we look at the Java runtime layers, there's something that we can do to improve things. So basically reduce as much as we can the size of that layer. And we can use JLink. JLink is not new. JLink has been added in Java since JDK 9. And basically the goal of JLink is to create a custom runtime that will only carry the modules that are needed by an application. And quick tips here, your application doesn't have to be modularized to use JLink. So this is an example. So this example is basically a serverless Java function. Those figures, those numbers are based on OpenJDK 13, but they shouldn't change a lot. So if you look, a whole OpenJDK 13 weight over 300 megabytes, that's really a lot. Now, if you create a runtime with all the modules, you will have a runtime that only weighs 168 megabytes. So that's basically 56% of the whole JDK. So that's already a huge win. Now, it doesn't really make sense to create a runtime that includes all the modules because there is no way you can create an application that will use all those modules. So what you want to do, you want to use JLink as it was meant to. You want to create a runtime, a custom runtime that only includes the modules that are needed in this case for this serverless Java function. If you do that, you will go down from 178 to 15 megabytes. That's a huge difference. Then you can also remove some information that might not be needed at runtime, such as the main page, the header files, and you might also want to strip the Java debug information. If you do that, you will go down from 50 to 44 megabytes. And last but not least, you also have the ability to compress that custom Java runtime. So there are two levels. Compress one will go from 44 to 37 megabytes. And if you use a compression level 2, you will go from 44 to 34 megabytes. So basically, by using JLink, you can create a custom runtime that is way lighter. So this is, in this example, we went down from 316 megabytes down to 34 megabytes. So that's a huge win in terms of reducing the size of the Java runtime. And again, your application doesn't have to be modularized. Now, if we look at the operating system layer, what can we do? Well, the basic idea is to leverage and use an operating system layer that is lightweight. So most of the distribution have two variants. One that is the complete one with all the bell and whistle, and most of the time there is also an equivalent which is a slimmer. Now, one advice, it's not because there is slim in the world of a distribution, of a Linux distribution, that it's lightweight. You should really look at the size. So the basic idea is to try to use a Linux distribution that is as lightweight as possible. So directly, Alpine comes to mind. So Alpine is a security-oriented Linux distribution that is also very lightweight. Now, Alpine is relying on Muscles. Muscles is an alternative to libc. Libc being the C library that C++ code used to talk to the underlying Linux kernels. So Hotspot, being written in C++, is using glibc, and Alpine require Muscles, which is a different, it's an alternative to Muscles. So it doesn't work out of the box. The good news is that there are multiple things that we can use. There's this Alpine package glibc, so it's basically an intermediation layer between Muscle code and glibc, so that you can run glibc code on top of Muscle. So the thing is that, well, I'm not very fond of that approach because it's basically an intermediate layer, so it has a potential issue, and also it had weight to the image. So basically, well, we are losing some of the benefit of using Alpine. And then there's Project Portola. The goal of Project Portola, so it's an OpenJDK project whose goal is to run, so build basically OpenJDK on top of Muscle instead of libc. So with the Project Portola OpenJDK build, you take them and you can run them directly on top of Alpine. Now you see that there is a small asterisk because Alpine is well, not officially supported in the sense that we are doing the OpenJDK builds, but they are not going through all the testing that other builds are going through. So at this stage, we don't recommend to use them into production. The good news is that this is about to change because there's this new JEP, Alpine Linux port. And that JEP is targeted for JDK 16, so the next release of OpenJDK. And basically, this is about bringing the Alpine port, so Project Portola, into mainline. And if that works, that basically means that we'll have Alpine OpenJDK builds that we can use as any other builds. So let's have a look at a demo. So when I do a demo, people are often asking me to show real life server application. So for this demo, I'm going to use a server and I'm going to use the Minecraft server. So I'm going to basically wrap I'm going to wrap into a container the Minecraft server, and for that I'm going to use JLink and Alpine operating systems. Okay, let's see. So ls clear. Sorry, it's clear. So what I have here, I have the Minecraft server, and I have a Docker file. If we look at this Docker file, it's a multi-stage Docker file, so it has two stages. So this is the build stage, and this is the second stage. So we see that this one is using OpenJDK 16 Alpine. It also uses the JLink command to create the custom runtime. So basically how JLink works, so JLink, I'm going to use compression level 2, and then this is where I want my custom runtime to be put, and then I just need to specify which modules are needed by my application, in this case the Alpine runtime. And then the second stage, we take this base image, Alpine, we create the directory, we copy all the files that are needed by the Minecraft server, including this license. And then we simply take from the first build stage the custom runtime that we have built, and then we run the Minecraft server. So let's build that. So docker build minus, let's call it mine, and okay. So this is built. So we can now check using this little utility, this image. So this is the Minecraft image, container image that is using Alpine and JLink. So let's first, so okay, so those are the different layers. So the first one is 4.6 megabyte, that's the Alpine operating systems. 181 megabyte, you can see on the right, that's the license file. Then we have these property files, which is 1 kilobyte. And then we have this 36 megabyte, which is the server .jar. So that's really the jar of the Minecraft server. And finally, we have this, well, let's say 16 megabyte layer, which is the custom runtime. So we can see here that this is our custom runtime that has been created by JLink. So it has all the modules and just the modules that are needed to run Minecraft. And basically, we can see that by doing that, we have a Docker image that weighs less than 100 megabytes. So it has everything from the operating system, Alpine, it has the Java runtime, and it has also our code, in this case, the Minecraft server. Obviously, that's something which is key when it comes to starting up that container image. Okay, back to the slides. Very quickly, so this slide shows the settings that you can do using the different JLink options. So the Minecraft server needs 12 modules, so that weight with 1388 megabyte. If you are stripping the debug information, you will save from 88 14 megabyte. If you are using compression 1 from 88, you will save another 18 megabyte, and so on and so on. The thing that you might see at the end, if you remove the header file and the main page, you will not save anything. Why? Because in this particular page, in this particular case, I'm using the OpenJDK builds from on Oracle Linux, and they don't have the header files nor the main page included, so you're not saving anything. Something that you need also to keep in mind. This slide shows a JLink custom runtime, OpenJDK 13 in both cases, but using different builds. The first one is the Oracle OpenJDK build. The second one is the OpenJDK 13 builds from Debian. Those two runtime are using one single module, the Java-based modules. One weighs less than 15 megabyte and the other one weighs nearly 500 megabyte. That's a huge issue. Why? Because the second one, the Debian OpenJDK builds, include by default the native debug attributes. The good news is that since JDK 13 you can remove, so you can strip out those debug information. If you do that, you will have a build that weighs a more reasonable 51 megabyte. So that's something to keep in mind as well. Okay, let's talk about the latency, but this time, so we've talked about the latency, some tricks that we can use at the container startup time. This time we're going to move higher and we're going to discuss some of the techniques and things that we might want to do at the Java layer. So basically trying to improve the startup time of the Java code within the containers. My first advice is the following. So this slide shows the startup time between Java 8 and 9. And clearly we can see that in Java 9 we had a big regression. My advice, try to use the latest Java version, because there is an ongoing effort to try to reduce the startup time of Java application. So that's the basic, the most simple advice I can give. Try to use the latest Java version if you are concerned about the startup time. Obviously, there are many other benefits to use the latest Java version. So something else that I want to quickly discuss is CDS, class data sharing. The basic idea of CDS is the following. So whenever you run a Java application, the virtual machine will have to load the class, and basically will have to do a lot of things to basically from the class file on the disk to load them into something that can be used by the JVM. So basically from the disk on representation to in-memory representation, there are a lot of works going on. And obviously, this has to be done each time the application starts. And not only that, obviously an application has a lot of class. So that work has to be done a lot of time. CDS is basically about taking a snapshot of the class, of the in-memory representation of the class, so that the next time the application starts, the JVM can directly put from disk that in-memory, that snapshot into memory. So basically we don't have to go all those operations again and again. And this obviously reduces the startup time. So let's have a quick demo. So let's see. For that, I'm going to switch to Linux. So I have a Linux instance running on the Oracle Cloud, if it's the right one. Let's see. Yes. So I still have this simple hello world application that just displays some information about the environment it runs on. So I can run it. So hello, let's see. Yes. So basically this time I have a Java 15. This VM has 4 cores, so, and it has access to that much memory. It doesn't really matter. So I'm gonna compile that class, and we're gonna run that class, that application. Okay, we're gonna run it 42 times. So I have this little perf 42 that's just basically an alias to perf to invoke 42 times some code. And the first time we're going to switch CDS off. So this application is invoked 42 times, and on average, the time it takes to invoke it is, let's say 200 milliseconds. So next, I'm going to do the same, but I'm going to enable CDS. So 42 times without 200 milliseconds, with CDS enabled 145 milliseconds. So that's a huge win. We went from starting this simple application to 200 milliseconds down to 145 milliseconds. And I'm going to share another tricks. To enable CDS, you can use xchar on, or you can just do that because CDS is enabled by default. And again, we have the same result, 145 milliseconds to start that. So that's something that you should really look at when you are using Java code running into containers. Now, the application, the samples that I've used is pretty trivial, so the benefits were huge. But when it comes to real applications, CDS brings also benefits. So this is a tweet coming from the maintainer of JRuby, and basically, if you look at the numbers that Charlie has published, just look at the bottom lines. So they went down from 153 milliseconds down to 717 milliseconds. So, and JRuby is a real-life application. I mean, it's a Ruby interpreter written in Java, and there is a very complex machinery behind it written in Java. So you should really consider to use CDS whenever you are running Java code into containers. And the good news is that CDS keeps evolving. Now you also want to look at your tooling, because more and more tools are also simplifying the CDS usage. For example, when you build a JLink application, CDS will directly, by default, build the CDS archive for your Helidon application. So that's also something that you need to look at, the tooling that is evolving around CDS. Okay. At the Java layer, to speed up the startup time of Java code, we can go further than what we are doing with CDS. And one thing that we can look at is GraalVM, and more specifically native-image. So GraalVM is a high-performance polyglot virtual machine developed by Oracle Labs. It has many capabilities, including capabilities that are not for Java developers. So we will just look at one capability for Java developer today, and that's the native-image capability. It's basically an AOT compiler. So for that, I'm going to switch to a demo. So let's see, I'm going to go back to my Mac, and I'm going to switch to a different JDK version. So let's see, shell. I'm going to use this one. So it's 11 Java minus version. And this is indeed a GraalVM build. So let's see, we have this. So Java C, we're going to compile this simple hello world application, and so I have a class hello to class. So we'll see I can run it. But what I'm going to do, I'm going to use native-image, and I'm going to pass it the class. So hello to native-image. So native-image is starting, and let's quickly go back to the slide because this takes a few seconds. So what is happening right now? So I gave to the native-image tool from GraalVM my application. In this case, it was a single class. So the native-image tooling will basically look at all the different code within that. It will eliminate all the dead branches, and what it will produce at the end is a native executable. So basically, an executable that will contain everything needed to run on a given target, in this case on OS X, my Java application. So there's no external Java virtual machine. Everything will be baked within one single executable. So if we go back to the demo, it took, for this simple application, it took 45 milliseconds. And if we look what we have here, we now have this hello2, which is hello2. It's a OS X executable, and its weight 8 megabytes. I can obviously run it, what we see is that that code thinks that it runs on top of a Java virtual machine, 11 in this case. There is substrate VM, which is some sort of VM that is directly embedded within that native executable. So there's no external virtual machine needed to run that code. And obviously, if we look at the startup time, so that starts very quickly. Obviously, if we compare that to time Java hello 2, so this time I'm running the same code, but this is the class. So this time I'm running on top of the Java virtual machine, and you see that the startup time, well, is different. So this is the native image in action. So let's go back to the slide. Now, on the plus side, GraalVM-native-image will give us a native executable. So no external dependency, nothing is needed, no virtual machine needs to be installed. We have one single executable that is super lightweight versus what we would have on the pure Java side. And obviously the startup time is greatly improved. But there are some limitations. So for example, one of the limitations that there's today is the fact that only Java 8 and Java 11 are supported. And we have just released Java 15. So they are trying to catch up, but they're not there yet. There are also some issues. For example, you cannot use the native VM interfaces. Serialization also is not allowed. So there are a bunch of limitations, and all those limitations are documented in the links that we have on this slide. Now the good news is that there's a new project called Project Leiden, whose goal is basically to bring into OpenJDK this concept of native image. So native image being basically an executable that will run on a given platform. Another limitation of GraalVM and native image later on is that obviously once you have these, in my case I had an OS 6 executable, the Java portability is lost. So if I need to run that code on Linux, I would have to build on OS 6, but also on Linux. I cannot just pass around the executable that is produced. So the good news is that Project Leiden is basically looking at bringing that native image capability, that native image concept into OpenJDK. So this is a fairly new project. It has been announced a few months ago. So right now there's nothing yet, but things are starting to evolve on that front. Okay, something else that I want to quickly discuss is when it comes to performance is all the investment that we are doing on OpenJDK are also leaking when you are using OpenJDK within the containers. So basically this slide shows the improvements that are, well, this slide shows that for G1 GC there have been over 700 enhancements that has been done since JDK 8. And obviously using G1 in the containers, you will also get access to all those improvements. This is an example of the native memory consumption. So with G1, to manage 16 gigabyte heaps, on JDK 8, you need another 4 gigabyte to manage that 16 gigabyte heaps. JDK 11, that has been reduced to roughly 3 gigabyte, and on JDK 14, it's lower than 2 gigabytes. So this is the kind of improvement that you will also get whenever you are using OpenJDK, an updated version of OpenJDK within containers. So something else that I want to discuss, so we have discussed the startup time. I want now to discuss security. So running Java into containers, obviously security is also something that is important. So this is something that happened quite some time ago. So basically, given that OpenJDK is open source, some folks took OpenJDK, built it, and claimed that it was the OpenJDK 11 GA release before it was actually released. I mean, the source code is there, so anybody can take the source code, build it, and claim, okay, this is the GA version of OpenJDK. So obviously that's something that you have to keep in mind whenever you are deploying JVM into containers. Something else. So this tweet basically shows the vulnerabilities, the top vulnerabilities in the top 10 most popular Docker containers image. The good news is that Java is not there, so that's a good news, but the bad news is that probably Java is not immune. For example, some time ago, someone posted on a forum on the internet, and that person was asking where is OpenJDK 11 GA Linux 64 muscles. So that's basically running OpenJDK on top of muscles. And GA basically means the general availability version. Someone say, okay, there's this build, it's the latest one, so you can consider that this is the GA release. Even though there's no GA release of OpenJDK 11 on Alpine. And worse than that, if you look at where that build is stored, it's stored somewhere in a university in Austria, not even on HTTPS, and the checksum are basically stored on the same HTTP directory in a random directory of a university student. So that's pretty scary. But still, that people was claiming, okay, this is the GA release that you can use. The good news is that, well, now we'll have, starting JDK 16, an Alpine Linux port. So basically, what I want to say here is that you should really choose your base image wisely. It's pretty easy to take any random Docker image and build your stuff on top of that, but that's clearly something that you shouldn't do. Not only that, you should really consider which base image you are using, but you should also secure it. So choose your base image wisely. If you are using the OpenJDK latest from Docker Hub, you're pretty safe. Oracle Container Registry is also hosting the latest OpenJDK builds, so that's also a safe choice. But again, don't take any random OpenJDK image that you are not really sure where it comes from. And last but not least, you should also secure that base image. You can reduce the potential surface attack by using JLink. So basically, JLink will not only reduce the size of the custom Java runtime, but it will also remove the bits that are not needed. So that's a good practice from a security point of view, to remove any bits that are not needed. Use a supported Java version. Make sure that you are using a supported virtual machine and not like I did in my example. I was using a very old Java virtual machine, because obviously, well, vulnerabilities are probably not fixed in that very old JVM version. And then I would say it's basically a container as usual. So you should secure a container running Java virtual machine as you would secure any other containers. So watch out about the certificate that you're using. Use toolings. There are a lot of toolings that you can use to scan your containers. Docker has, for example, a partnership with Snyk those days. So you can do directly a Docker scan to check for any potential vulnerabilities within your containers. Though that is not really tied to Java, but that's something that you should do regardless of if it's Java or not. Something else that I want to quickly mention is rootless containers. So it's something which is quite new, and it's basically something, the idea is that you don't want to run any container as root. For that, you probably want to use CGroups v2. CGroups v2 are not really new. They are in the kernel since 2014, but it's only recently with software such as Podman that CGroups v2 are getting adopted. JDK 15 had support for CGroups v2. So CGroups v1 is what we have been using for years, and CGroups v2 are now also supported on JDK 15. So this is transparent. Having said that, you should check out the issue that I mentioned at the bottom of the slide, because there is an issue with CGroups v2 if you are using Docker desktop on Windows, non-OS 2 and OS 6. And obviously that issue will be fixed. But as of today, that issue is still there. As of September, that issue hasn't been fixed yet. Something else that I want to quickly mention is there has been some recent change regarding Dockers. Two big changes. So basically, Docker will purge images which have been inactive, and I think that's a very good news. So basically, an image that has been pulled for, I think it's 6 months, will be removed. It will be purged. So basically that will forbid us from using very old Docker image. So Docker image containing virtual machines, which has not been updated for more than 6 months, they will disappear. So that's a good news. Something else which you should also look at, it's not really tied to security, but that's something that might break your Java application, is that they are also enforcing some pull rates limits. So for example, if you are an anonymous user, you can only do on a given image 100 pulls per 6 hours. So obviously that might break some build systems. I'm not going to spend any details on that. There is a link to that announcement, but that's something that you need to keep in mind if you're running Java and non-Java application into containers. So I think it's time to wrap up. So let's see, yes. So today we have discussed why it's important that the Java virtual machine behave as a good container, as a good citizen in the containers. Why? Because of the ergonomics. We saw that if the JVM is not aware that it runs with the containers, it will behave very strangely. It will probably not configure properly the garbage collector to use. The command for join pull will not be configured properly, and so on and so on. And at the end of the day, if we have Java code running on top of that virtual machine, chances are high that it will be killed. So the JVM will be killed by the container runtime, because the JVM is trying to access more resources that it has access to. We have also discussed tips and tools that we can use to basically reduce the latency of the startup time of the containers. There are 2 angles. First, we focus on the container startup time itself. So the idea was to reduce the layers size of the Java runtime layer, the operating system layers, and the Java application layer itself. And then we also discussed some techniques and tools that we can use to reduce the startup time of Java application, from, for example, CDS, to simply switching to a more recent version of the JVM, to also using native image from Graal, for example. The takeaway is that all the investment that we're doing on OpenJDK are also leaking into containers. So obviously, the advice here is to use a recent version of OpenJDK. So not only you will have access to, for example, CGroups v2, but you will also have access to the new Java language features, such as records, for example, such as text blocks, and so on and so on. And obviously, records in themselves, text blocks, are not tied in any way to containers, but still they are pretty useful to develop Java code. So basically, all the investment that we're doing are leaking into containers. And obviously, if we look at a big future investment that will happen in OpenJDK, that is very relevant for containers, that's Project Ladens. So basically bringing this notion of static image into the Java platform. So that's something that you should watch out. So finally, to close, my advice, please choose your base image wisely. And not only that, secure that base image. Use the latest Java version, and please never use Java latest. That image is very old, and you saw that if you are using it into a containers, well, chances are high that you will have issue very shortly. And please only rely on actively supported JVM version. All of them are container aware. Now, you might find some literature that still use these use container support flag. You don't have to use that anymore, because all the JVM those days are not only container aware, but they are also container aware by default. So you will only use that specific flag, in fact, if you want to disable the container support. So if you want to explicitly disable container support, you're going to use container support flags. Obviously, you need to know what you are doing in that case. And last but not least, please use a Java runtime instead of full JDK. Not only it will reduce the size of your Java image containers, but also that's a good practice from a security point of view to basically remove everything that is not needed. So please have a look at jailing. And again, jailing doesn't need, your application doesn't need to be modularized in order to be used with jailing. So that's something that you should really look at. And with that, I'd like to thank you for your time. I also want to invite you to check Inside Java. That's a new site where we put everything related to OpenJDK. And we have also put on Inside Java a new podcast called very creatively inside Java podcast. So you go to inside.java/podcast, and there we have a podcast that basically discusses everything OpenJDK and everything Java. So please check that out. And again, I'd like to thank you for your time. Thank you.